Welcome to this primer on relations. In this lecture, we'll introduce the notion of a partition of a set and connect that with the notion of equivalence relations. And in fact, we will show that they are basically the same concept. So let's recall. If tilde is a relation, we say, so tilde is a relation on a set X. We say that tilde is reflexive if everything in X is related to itself. Symmetric if you can switch the order of relations. Transitive if this holds. And we say tilde is an equivalence relation if it is reflexive, symmetric, and transitive simultaneously. Okay, let's move on. Here are some problems for practice. This one is marked as star not because this is hard, but because I'm going to, sort of use it. I should have given this earlier, but I'm giving it now. So it just says something about when is a function a bijection. And it's in some sense a tautology. Anyway. So let us define what is a partition. Suppose X is a non-empty set. Then first we will define a finite partition. So a finite partition of X is a collection of non-empty subsets of X such that two things happen. First, union of everything is X. And second, if you have two distinct things, then they are disjoint. So I write it this way to allow for the possibility that there may be repetitions here. After all, this is a set. So in a set, you can repeat the occurrence of an object and it does not alter the set. So it is possible that A1 is equal to A2 and I would still consider this a partition because after all, a partition is a set. So whenever you have two distinct entries, they are disjoint and the union of all the entries is the parent set X. So that's the definition, but let's see it through a picture. So if I have this blob denoting the set X, then a finite partition can be visualized in this fashion. So each of these are parts, and the collection of all the parts constitute a partition of X. So this may be A1, A2, A3, A4, A5, and A6. Okay. And you can see that the union of all these things is the entire set X, and if you pick two different things, they do not intersect. That's a finite partition because there are only finitely many things in it. So let's see an example. So let X be equal to n and A0 be defined as those natural numbers which are even and A1 is those natural numbers which are odd. So then this is a partition. Okay, so that's a very simple example. So let's continue. So now we will define the notion of a partition, nothing to do with finiteness. So again, X is a non-empty set, then a partition of X is a collection. So a collection of subsets of X, I will write that, but here the indexing set could be infinite. This J could be infinite and that is indexing our subsets of X. So it's a collection of non-empty subsets of X such that, again, two conditions. First is that the union of all of them is the entire set X. And the second is, if you have two distinct things, then they do not intersect. And it would be difficult to draw a picture for a true infinite partition. So I won't do it, but I will give an example, a very trivial example. So X be any set, then is a partition. Right? It is a trivial example because all we have done is collect every point in a singleton and put all the singletons in a single box. That is obviously a partition. Okay, just check if you're not convinced. Just check these two conditions. Okay, so that's the notion of a partition. It's a very natural notion. The phraseology is also well chosen. And now let us see how partitions are related with equivalence relations. So suppose we have a partition pi. Generally, partitions are denoted by pi or tau, etc. So suppose pi is a partition of a non-empty set X. Then we define a relation, which I will discuss pictorially, but let me first write the formal description. So we define a relation on X as those ordered pairs such that there exists an element in pi with the property that X and Y are both in A. So what's going on? We have our set X and some partition has been given. I can only draw a finite partition, of course. And now, suppose you have an element X here. What is it related to? What are all the things that it is related to? It is related to those things which share its part. So X is lying in this part, and all the things which are lying in this part are those things which are related to X. That's the definition. That's what we have written here. So this is our relation coming from the partition, and clearly it is reflexive. So this is reflexive. Why? Because, of course, the part in which X lies is the part in which X lies. So X tilde pi X, because after all, since pi is a partition, there has to be a part in which X lies, because the union of all the parts is the entire set X. So first locate the part in which little x lies, and then little x lies in the same part. So this is a tautology. It is reflexive. This is symmetric, because if this is the case, then what happens? So that means there is some element of pi which contains x and y, and hence there exists an element of y which contains y and x. Again, a tautology. Right, and finally this is transitive. So this I leave as an exercise. And therefore, whenever you have a partition, you get an equivalence relation from it in a natural way. Okay, let's move on. So now we will define the notion of an equivalence class. Suppose X is a set and tilde is an equivalence relation on X, and fix an element in the set X, then the equivalence class of little x is defined as, the notation is just a bracket and put x inside, and if you want to emphasize the role of the relation, you put a subscript tilde. Alright, and what is the definition? This is those things which are related to x. Okay, it's a very simple definition. Alright, so now here is the thing. First of all, so what we claim is the union of all the equivalence classes is the entire thing. And this is trivial because if you choose some element in your parent set, then this belongs to its own equivalence class. Why is that? Because this is a reflexive relation. So little x is related to itself, and hence this is the case, which implies this belongs to this guy, and we are done. So this claim is proven. Second is, if you have two distinct equivalence classes, then they do not intersect. So why is that? So suppose we had intersecting equivalence classes. This was the equivalence class of x, and this was the equivalence class of y. and suppose an element z was common to them. So let's say x was here and y was here. Then, since x is related to z and z is related to y, by the fact that tilde is in particular transitive, we see that x is related to y. And therefore, everything that is y is related to is also related to x, again by using transitivity. Right? So once again, since z is a mediator between x and y, x is related to y. So x tilde y comes to us. And now if y is related to anything, we see that x is also related to that thing. Hence, everything that is in the equivalence class of y is contained in the equivalence class of x, and everything that is in the equivalence class of x is contained in the equivalence class of y. So that's it. That's the proof. So this implies that. So then, it would follow. Let me not write anything. So from this, if you assume that this is not true, then it follows that this is not true, and hence the contrapositive. So both these claims are proven. So the result is that for any, is this a vertical line? Probably is. Yeah, so for any equivalence relation tilde, the set of all the equivalence classes, which is denoted by x, then we put a slash and then tilde, and how do we read it? We read it as x mod tilde. This is how we may read it. Okay? So this is a partition of x. That's what these two claims give us. Right? So previously we saw how a partition gives rise to an equivalence class, and now we see how an equivalence class gives rise to a partition. So now we will finish everything. Yeah, so there is no need for this slide. I just mentioned that. So now, suppose x is an empty set, and this is the collection of all the partitions of x, and this is the collection of all the equivalence relations on x. Right? So now what we have is we have our map, which capital phi, which is from partitions to equivalence relations. And how is it defined? It takes a partition and produces an equivalence relation that we saw. We denoted it by tilde pi. And then we have this guy, which takes an equivalence relation and gives us a partition. And how is this defined? This takes an equivalence relation tilde and out all the equivalence classes. Right? And now here is your exercise. Show that this is identity. So this identity on pi x, of course. So this is an exercise. And similarly, the other direction. So you also have to show that this map, which is psi, and this map, which is phi, this composition is also identity. Okay, so these two are exercises, and therefore once you do those exercises, you see that psi composed with phi is identity on pi x, and phi composed with psi is identity on ex. I think I miswrote. So psi composed with phi is fine. Yeah, this is fine. So this is what you need to show, and therefore both of these are bijections. Okay. This is by the star marked exercise. Just look at the star marked exercise and you will see. So both of these are bijections, and therefore there is a quote-unquote natural way to identify a partition with an equivalence relation and an equivalence relation with a partition. These are natural identifications. Okay, so with that I want to end this lecture. As usual, like, comment, share, subscribe, and I'll see you next time.